So we're going to look at the Hartzell HC3 or HC-B3 series of propellers. The TN is what's on the King Air with the PT6. We'll also look at the same propeller in regards to the TP331 when we look at the fixed shaft turboprop. So some general info on these Hartzell naming things. This is straight from like the TCDS. And again, this is the B90 example, but these are common. These are the same props that have been used on pretty much all the King Airs through the years, and quite a few other aircraft that use the PT6 engine, which is probably the most common turboprop. It is the most common turboprop engine out there. But just a few things. So HC is Hartzell controllable, so that means a constant speed propeller. Their B is their basic design, which is just kind of their in-house. They're like nothing too special about it. Okay. 3 is 3-bladed. You'll also see HC-B4, HC-B5, which are 3-bladed. HC-B3 is 3-bladed, 4 is 4-bladed, 5 is 5-bladed. But the guts of the prop and how it operates are the same, essentially, no matter which category it is. Blade shank size, again, that's more of a Hartzell reference for a series of blades. So you may have the same hub, and this is primarily the hub part number that we're looking at here. The blades will have their own part number, and then the full buildup will have a different part number. But over the course of the lifetime of one of these, the blades that originally came with a hub or came with a prop may not be the ones that stay on it its entire life. And so that could potentially change. These are all flange mount. The N there, after the T, the N is flange mount. And then N, there's several different flange mounts, but the N is for 8 9/16 bolts and a couple dowels. And then the -3 afterwards, you can see there's a list of codes for that dash number. So 3 is external beta feedback, which we'll look at in just a minute here. No start locks for base model. So the start locks are what hold it into a fine pitch position if it has it. Since this is a free power turbine, it does not need the start block. So it's going to, when it's shut off, it's going to live in a feathered position. When we look at the TP331, that propeller, that's a fixed shaft turboprop, that one is going to have the start locks. And so that's going to be like a -5, for instance. Okay, you can see the -5 includes start locks, but they can modify them beyond that. So, of course, not everything's 100% all the time. You have to read through the entirety of it. And then finally, the last part there, in our case, the B at the very end. Any other character is a minor change, so it would be like a mod A, a mod B, a C, right? Each time they make some kind of a minor modification, they tack that on at the end. The other example that's shown here, the one that's on the TCDS, they put that AL there. L is for left-hand rotation. So if you they do make versions of this propeller that can turn left-hand. There also is the ability, for instance, you can have a -2, a -3, or a -7, where there's no start locks in the base model, but then if they put a Y at the end, it means it does have start locks, even though that model designation doesn't say it. So when you're looking at these and trying to figure out what they are, sometimes it takes a little bit of decoding, and the same information might be in more than one location. But these are a steel hub, very similar to the other Hartzell steel hub propellers out there. They use aluminum blades, so it's a fairly simple design, pretty straightforward design. Newer propeller models are going to be where you get into things that have like composite blades, for instance. And then pitch control. These have counterweights that take the propeller blades to the high pitch or the high angle of attack up to a feathered position. They also have a feathering spring to assist that. And then governor oil is routed to a piston. It's got a dome with a piston to do your low pitch control or movement to low pitch with a max pressure of 500 psi. These props are feathering and reversing, although there is a series, if you have these, the dash 2 right here. If you had a -2 at the end, it says no feedback mechanism. That's because they're non-reversing. So the earlier versions of these, they did make some that were non-reversing. But most of them that you'll see today are going to be reversible. So feathering, reversing, right-hand rotation because it doesn't have the L in there. And then we have de-ice boots, de-ice boots along the inboard portions of the leading edges. Okay. When we mate these to a PT6 turboprop, we're using them with a engine that's been around for a long time. These were first certified. The first PT6s were certified in 1962. And they've made over 60 different variations since then, ranging in horsepower. Those early ones had a shaft horsepower of about 500 horsepower. Your latest ones are somewhere in the close to 2,000 horsepower range, 1,940 shaft horsepower. And so they've made them larger. Part of that is as they've gone larger, this image, for instance, is showing one of the slightly bigger ones because it's got a dual stage power turbine here driving the propeller. So the earlier ones had a single stage power turbine driving the prop gearbox. The later ones, as part of that additional power, are a dual stage power turbine. However, they all still have a single stage compressor turbine, and there's several variations of either 3 or 4 stages of axial compression with a centrifugal compressor right behind it. So max speed on these propellers run at about 2,200 RPM, and that puts the tips just under the speed of sound. And they can be in single or multi-engine applications, like you can see here. So you've got things like the King Air up top here, and that's got the 4-bladed. That's the HC-4 version of the propeller. Okay. Here's the Cessna Caravan high wing. That's a Piper Meridian. I'm not quite sure what that top left one is. That was one Jeremy gave me. But I'm not sure what it is. Some kind of a twin cargo thing. So a little bit simpler schematic. What you have, free power turbine, remember, means the propeller is in no way connected to what's called the gas generator, the area made up of the power turbine and the compressor. Sorry, the gas generator turbine and the compressor. The power turbine or free power turbine drives the gearbox and drives the gear. It drives the propeller. And the big key here, and where it becomes important with our propeller, is that the prop itself does not apply any kind of a load to the starter. So when one of these engines are being started, the gas generator area, the engine turbine and the compressor, are going to be rotated by the starter directly. These also drive the compressor, the turbine, the engine turbine, or gas generator turbine, drive the accessory gearbox, so a separate gearbox that runs accessories, and that's what the starter is attached to. And so ultimately, you don't need that latch mechanism to hold the prop from going to feather shutdown. We're okay with the propeller going to feather because it's not going to drag down the engine during the starting process. So common traits with these type of turboprop propellers, 3, 4, or 5-bladed models, they all use a steel hub and constant speed reversing feathering, minus, like I said, some of the older ones, some of the very early ones, the -2 models didn't have that reversing function. They were still constant speed, they were still feathering, but they didn't have the reversing ability. Those were back on like a King Air model A90, which was early 1960s era. Flange mounted, we talked about spring loading, counterweight to feather, and then oil pressure to decrease the blade angle. And so now we're going to look at how the operation is. How does the engine and the components on the engine interface with the propeller in order to make the propeller do what we want it to do? Because it's this one, and the reason I start with this one is very, very similar to what you've seen on reciprocating engine aircraft. It's almost like a big version of a reciprocating aircraft. When we go later on, we'll add there's some additional components in some of the propellers, these turboprop propellers used on bigger aircraft, where they actually, in some cases, can use oil to go to coarse or fine pitch. And they may have a coarse and a fine adjustment as part of that. And they might have, and then they have to have some kind of a feedback control mechanism. This one does. This is an external feedback control, which is kind of added to the outside. But the propellers used on the TP331 and then bigger engines all goes to an internal system that this does not have. So it's kind of a segue into those bigger propellers. The propeller governor on something like this is similar to your constant speed governors that you find on your recip engine aircraft. Okay? It has the same flyweights acting on a set of speeder springs and pilot valve that you would have in any other constant speed prop aircraft. So flyweights, again, just like they when we're in an underspeed condition, that speeder spring is going to push down on the flyweights. They're going to be pushed in. Okay, that's going to push the pilot valve down to push oil, to allow oil to go to the propeller, to move it to a finer pitch and speed up. If we're in an overspeed condition, those flyweights moving out are going to overcome the speeder spring. They're going to raise the pilot valve, and that's going to allow oil, when this is raised up, oil will be able to come back, and this piece will be raised up here, flow back, and out to the reduction gearbox. Okay. Engine oil supply is coming in over here. We've got a dedicated oil pump inside of here. That's where that high pressure, that up to 500 PSI comes from. Okay, it doesn't just use the oil pressure from the engine itself. The engine oil pressure is probably running somewhere around 30 to 60 PSI. So we're boosting it to a much higher pressure here inside the prop governor. But something that's addition here that you're not going to see on your recip governors is something called the beta control valve for what are called beta modes of operation. I'm going to go into detail on those, but in summary, you have alpha and beta mode. Alpha mode is your higher power. It's basically your flight idle and above. Beta mode is anything from below flight idle down to ground idle and even into reverse. And you're running in what's called beta mode. So kind of two general modes. So we'll look at how the constant speed governor works, kind of what we are used to during alpha mode. And then this beta control valve is what takes over during beta mode operations. So low power like ground operations and reverse. And the difference here is that this is operated directly by the power lever, whereas the input arm, the prop speed lever there, is operated by the propeller control in the cockpit. And so during beta operations, that propeller control lever in the cockpit actually really doesn't do anything. It's all done using the throttle. And then it also has the ability to route governor oil to or from the propeller. Okay, so instead of, like I say, it essentially bypasses that whole automatic mechanism and allows the operator to directly control the prop angle along with the engine power. Some of the other items you'll find on these, we've talked about overspeed governors. And so when you have a turboprop, you typically have, like I said, two gearboxes. You have an accessory gearbox that runs things like the fuel pump, the oil pump, the starter generator, depending on the design. Those are all run off the accessory gear. The prop gearbox then is going to be spinning the propeller, but then we've got a few other things running on it in order to control the propeller. And so the prop governor is run on that prop gearbox. In addition to that, there's going to be typically an overspeed governor, and that's mounted here, and that's picking up. This one's actually piggybacked, so you can see the prop governor in the lower part of this picture. It's actually piggybacked on top of, this is what's called a tach generator right here, or a tachometer generator. That generates an AC signal to give a prop speed indication in the flight deck. So they piggyback them on top of each other. But the overspeed governor, if the prop exceeds 110% of its rated speed, so on a lot of these, that rated speed is 2200 RPM. So you're at, so if it exceeds 2420 RPM, that is going to essentially port any oil pressure in that prop dome back to the accessory, or back to the propeller gearbox. And when that happens, those flyweights and spring will push it to a higher pitch condition and will slow the propeller down. The increase of the blade angle decreases prop RPM. There's also a power turbine governor. So this is on, if you look on like our King Air, this is on the right side. Okay, a separate governor down here is the power turbine governor. And this is looking at a similar thing. It's looking at RPM in that gearbox, in that accessory gearbox area. But now this is more of a protection to prevent if there is a, particularly if there is a propeller failure and there's no longer a load on that free power turbine. We had this happen at the airline where one of our planes hit a deer on takeoff and it basically sheared all the blades off the propeller. You can imagine that would be able to spin up really fast. You lose all that extra inertia from the blades. And in that case, what now you're worried about is you do not want that you don't want that free power turbine to suddenly just go absolutely crazy RPM wise. Because at that point, that's going to fly apart and become, it will burst out of its casing. It will send shrapnel out of the engine. It grenades itself, to put it. Yeah. And so a power turbine governor is looking at that. And if the RPM gets too high, exceeds, and I don't, the power turbine RPM at 105%, that will reach, it doesn't have to get up to 105% to get 110% on the prop RPM. So if the prop RPM has, because it can kind of freewheel in there. So if the power turbine is hitting 105%, what this essentially does, it's not, at this point, we're saying, okay, for some reason the prop is not putting any load, or it's not putting enough load on that power turbine. And by that point, hopefully the overspeed governor, the prop overspeed governor has already tried to put more prop load on that power turbine. And if that fails, because say blades got sheared off by a deer getting hit by the engine, by the propeller, then this will kick in, the power turbine governor will kick in, and it will prevent, or it's supposed to help prevent that power turbine from grenading itself by essentially, it sends a signal back to the fuel control for the gas generator, which it's pneumatic in this case. It basically drops a pneumatic pressure. It makes that, it tricks the fuel control into basically cutting the fuel down significantly that's going to the gas generator. And so that slows down the gas generator. It reduces the amount of combustion exhaust gases that are coming out of the gas generator and subsequently going through the power turbine. And so when you don't have those gases, that large amount of exhaust gases going through the power turbine, now the power turbine is going to slow down without having to put an additional load on. So basically it cuts the fuel off in order to prevent the rest of the engine from overspeeding due to a sudden loss of load on the engine. This isn't controllable in any way. It basically just, it's set. It does have a test. You can see it does have this set of wires coming up to it. They do have a test function on them, just like the prop governor or the overspeed governor up here. That also has the ability to be tested. And both of those work with flyweights, some kind of a speeder spring, and then in the case of the prop overspeed governor, when that activates, it dumps the oil pressure. It's another way to dump oil pressure. When the power turbine governor activates, it dumps, or it releases air pressure from a signaling line that goes to the fuel control. The engine fuel control, I don't have a picture of it here, but it's mounted to the rear of the accessory gearbox, so it's driven by the gas generator. Okay, and it's going to control the gas generator output as well as the power output. Okay, and the gas generator RPM that creates the gas generator. The whole point is to create that combustion gas to spin the power turbine to ultimately turn the gearbox and the propeller. And the more of that gas being created versus the propeller pitch, if you're at a higher pitch setting, the higher the power output of the engine. And the way we measure that is with torque. The amount of torque put on the propeller. But it is linked, in this case, mechanically linked to the beta control valve, which is what this linkage kind of shows here. It's linked to the beta control valve on the prop governor. And so that's how when the engine and when the aircraft, when it's in beta range, that power lever, instead of using the prop lever to control the prop and the power lever to control the engine, now you use the power lever to control both the engine, the gas generator, and the propeller simultaneously through that beta valve. And remember, that's anything essentially below flight idle and down into ground idle and then into the reversing range. It also is what's controlling blade angle during reverse. In order for that system to work with the beta control valve and everything, we have to have a way to know where the prop blade angle is, okay, for that to adjust things properly. So when we're in alpha mode, when we're in standard running mode, that feedback comes from the RPM and the flyweight position. But since those flyweights are no longer in the circuit, this has to have some feedback from the propeller, and that's what this what's called the spider and slip ring and carbon blocks. And so on the, let's see, get a picture of the front of the propeller here. No? Oh, put that in. On the front of the propeller, we have a spider-looking device that's connected to the blades. I'll pull a picture of this up in a little bit here. And that moves this ring right here, which is shown on this picture. It's kind of covered up by this arm. But it's this ring. And this arm that you see here, which is connected to that beta valve linkage, there's a carbon block running in it, in the ring, and this ring can move backwards and forwards. It's pushed or pulled by by what's called the spider, a linkage on the front of the propeller that follows the pitch of the blades. And then this can move back and forward, and it drags those carbon blocks with it, and that adjusts kind of the angles in this linkage up here to set neutral points during operation. And so it gives what's called proportional control of the propeller. So the more commanded input you give, or the more commanded reverse you give, as those blades move into that position, whatever you've selected with the power lever, when the blades get to the position selected by the power lever, this is what tells it to stop moving and stay in whatever position you selected. So it's a feedback signal. So what I mean by that is it's talking to, all this stuff is linked up to a set of 3 levers in the flight deck. Okay? And so you have on the left there is your power lever. And the power lever, as I mentioned, the engine can run in either an alpha mode or a beta mode. For what we do in maintenance, most of the time we're going to be operating in that beta mode unless we're doing some kind of a high power run. And so in the beta mode, we're directly adjusting fuel flow to the engine. And that's also going to adjust that propeller blade angle through that beta valve and that carbon block and ring, that feedback ring linkage I just showed you. And then it also includes our reverser operation, so prop reverse. And so what we're showing here right now, our power lever is in the idle position. That's these levers labeled A, left and right engine lever. Pushing them forward increases power. anything behind this line, you can see the back edge of it here. Anything behind that is going into a reversing mode. And to reverse, you have to lift up on the levers, and then you can start pulling them back into this area behind here. And you can see it's labeled reverse, and this is your full reverse. And the further you pull those back, it's kind of counterintuitive, but as the prop blades reverse, it actually starts to throttle the engine back up again. And the further you pull them back, the harder you pull them back, the more reverse thrust you're getting. As opposed to when you push forward on them, the more thrust you get forward. And the whole idea behind that is, think about what it's going to do to the airplane. Okay? So you pull them back, the harder you pull back, the faster you want to stop. It's kind of like, how many people ride horses? Anyone ride a horse? Anyone ever been on a horse? You pull on the reins, the harder you pull on the reins, the faster it stops. And if you keep pulling on the reins, they start to walk backwards. Right. I'm not like a big horse person. I'm talking like Boy Scout camp here, okay? My daughter's big into horses, but not me. We definitely don't have a horse. The other way, alpha mode is basically anything forward here, as long as power lever, as long as the prop or the fuel cutoff, what's known as the condition lever, is further forward. Prop controls are in the middle here. It adjusts the RPM in alpha mode. So if you're at those flight idle or above in those flight power settings, now the governor takes over, the prop governor takes over, and now it acts like a typical constant speed propeller, where these propeller levers provide an input to that prop governor. They move the arm and control the tension on the speeder spring. Right now, they're in the feather position. You can see they're all the way back, and they're in kind of this white and black crosshatched area. And they've been selected feather for shutdown. And then the third set of levers that you have there on the right, they're labeled G. Those are the condition levers. They're in a fuel cutoff position right now. And they essentially select, do you want the airplane, do you want the engines and the propellers to operate in a ground mode? Or do you want them to operate in a flight mode? Or do you want the engines to shut off? And so right now, they're in the shut-off position. What they do is they close a fuel valve inside of the fuel control. So it's not like a firewall valve. It's not the valve on the airplane that sends fuel, but it's another cutoff valve inside the fuel control on the engine. When they're in the low idle position, which is you moved up to right here, that's kind of your ground idle, ground operation. It locks the propeller into a beta mode operation. So your prop levers basically don't do anything other than they can put it in feather. You do have to move them out of the feather position. And then your power levers, that if they're in that low idle beta position, now your power levers are going to control both propeller RPM or propeller blade angle and power, the amount of fuel being sent to the engine. When they're pushed forward into the high idle position up here, then they go in high idle. It's still in beta mode until you start to bring the propeller lever or the power levers up. And as you add power to the engine and that prop governor kicks in and starts to treat it like a constant speed prop, then it is in alpha mode, and you can use your prop levers right here. You can actually adjust you set your RPM, your desired prop RPM. So a little kind of details of all that. So the beta mode of operation, 50 to 85% RPM. What happens below 50% RPM? Any idea? And this is engine RPM. That's gas generator RPM. What happens below that 50 to 85% RPM? Yeah. The engine shutdown. When the engine's running ground idle, its absolute minimum idle is probably about 50% of its total RPM that it can run. Okay, so that's why there really isn't anything below 50%. Getting from 0 to 50%, you're starting the engine. Okay? So these are always sitting at 50%. Unlike, a recip engine, where your idle speed might be 600 RPM, right? And it goes up to 2000 RPM. This, you're at the midpoint and above. You're doing nothing below that. So 50 to 85% RPM, ground idle to just above flight idle. That's what I was talking about. We move the condition lever to the flight idle position. The props speed up. The engine speeds up. It's running about 85%. And as we start to move those power levers forward, it's going to move out of beta mode into alpha mode. But if we're in that beta mode area, ground operation modes, power lever is going to control both fuel flow and blade angle. So you don't have to worry. You basically just leave your prop levers in high RPM all the time. But even though they're in high RPM, it doesn't mean they're always going to be in that high RPM position. They're going to be in the position selected by the power levers. So as we move the power lever forward, for instance, the cam on the fuel control increases fuel flow. It's also going to move that beta control valve up on the propeller governor. It's going to pull it out, what's called out of the governor body, which is going to start to release pressure from the propeller. So even though our prop's in high RPM with the prop levers, when we're in that ground idle speed, they're actually at a fairly low RPM. They're at a high pitch position. So as we bring that power lever forward, that oil pressure in the dome area is going to release, and that's going to, it's at fine pitch. It's going to start moving it to a higher pitch position, and then as it moves to that higher pitch position, it's going to drag that ring and carbon block assembly. And when it gets to the selected position by the power lever, then it's going to, that beta valve is going to reclose, and it's going to lock those props in that position, okay, for a given power setting. If the power lever is then moved back rearward, fuel flow is going to reduce. And here's that beta valve, for instance. Beta valve moves into the governor body, which is going to direct oil. So as this moves in, here's our oil pump. Oil is going to be, this is going to move this way. Oil is going to be able to travel through here. And it goes through this top spool and this is out to the propeller. So that's going to send oil to the propeller. Okay. When we went to the higher power setting earlier, that pulled the valve out. When it pulled the valve out, that allowed pressure from here to travel up through this and then back through here. And we would be in an underspeed condition. And so it allowed oil to dump back to the gearbox. Okay. So all right, because the prop's not going that fast right now. We're in a low speed condition because the engine's not driving it fast enough. So it's going to be, no matter what, it's going to think it's in an underspeed condition. And so when we reduce the power, piston's going to move out, decrease the blade angle, and then as the blade angles move to that decreased position, they move the carbon block in the ring, dragging the carbon block and that linkage that attaches to the beta valve, and it's going to close this back off again once the blades get to the position selected by the power lever. Bless you. Some of the other conditions, like I said, beta mode also includes reverse. And so in that case, the fuel flow is going to increase. But now the beta valve, the blade angle is going to go negative. And that's where we get that reversing thing going on. The face of the valve of the blade becomes the back of the blade. The back of the blade becomes the face of the blade. And now air is going to get pushed forward instead of back and provides that reverse thrust. And the further we pull that lever back, that power lever back into the reverse position, the more that blade angle is going to reverse up to its limit. And it's going to start to add fuel back, start to send more fuel to the engine in order to increase engine power to give us additional reverse thrust. So anytime during this beta operation, our prop governor is going to be in an underspeed condition. Because at this point, we're not moving fast enough at all for the prop governor to do its job. Okay, so it's out of the equation altogether. So these flyweights are going to be in, the pilot valve is going to be dropped down, and it's if the beta valve wasn't essentially controlling whether oil pressure went in here or not, it would be trying to port oil out to the propeller, but that oil, whether it's ported or not, is controlled by the beta valve. When we go to feather, the prop control is pulled full aft, and in this case, now what happens, a lift rod is actuated in the governor. And when that lift rod is actuated, you can see the flyweights have spun out here. It's actually lifted the input to the flyweights, and that essentially ports all oil pressure from the propeller down and back to, it essentially opens this entire spool valve up to allow oil to go back to the sump. And when we go into that feather position. Essentially it says, I want it physically lifts that whole mechanism and pulls that spool valve out of there and creates an open port for any oil pressure that was remaining in the propeller to go back to the gearbox. And the springs and flyweights that are on the propeller, the springs and counterweights. So we're not talking about the governor springs and flyweights here, but rather the springs and the spring that's inside the dome and the counterweights that are attached to the blades, are going to push those blades to the feathered position, and there will be no oil pressure in the dome at this point, and that will cause the blades will end up in a feathered position. And they will remain in that position as long as that prop lever is in the feathered position, which is lifting this whole spool valve up out of operation. So to unfeather the propeller, there's no way on a lot of these, there's no reason that we need to unfeather the propeller on the ground unless it's for a maintenance thing we can use like blade paddle. So there is no unfeathering pump or any other method to supply oil pressure unless the engines are running. If you want to feather it if you want to bring it out of feather, if you want to go to fine pitch on the ground, you have to use blade paddles or some other means of physically overriding those springs that are inside the dome. So to unfeather this prop, what we would do is we'd start the engine normally. And remember, it's feathered, but because it's a free power turbine, that prop's not putting any resistance on the starter. The engine can start, the gas generator can get going, and then the oil pressure will build, and at that point, then the governor or beta control valve, depending on what's selected, will take the propeller to the desired angle. In fact, when we shut down engines that have this type of a propeller, we take the propeller levers, we put them in feather for the shutdown process. So the blades go to feather. When we start up, before we even turn the engine on, we actually take those prop levers and we move them out of the feather position. But they don't actually move. The blades stay feathered because there's no oil pressure. As the engine starts, once it's up and running, for instance, in the case of like our King Air, we cannot run the oil pressure indication during starting. It runs on AC power and an inverter that will be damaged by the electrical spikes and surges caused by operating the starters. And so the way we know we have oil pressure during startup is by the fact that our props do come out of feather. If for some reason we didn't have oil pressure in the engine, our propeller would never come out of feather and we would shut down. So we use that as an indication as well. The overspeed governor works just like every other overspeed governor we talked about already. You can see it has the flyweights in here. It has a speeder spring, but there is no adjustment lever. It's just fixed. But if the RPM exceeds, in the case of these, upwards of 110%, 100 to 110%, depending on the engine and the aircraft it's on, those flyweights are going to swing out. They're going to overcome the speeder spring. They're going to raise this pilot valve here. And when that pilot valve is raised, oil is able to go from from the propeller and back out until, and that causes the blades to go to that higher angle of attack towards feather until they reach the on-speed condition. So it's not going to drop, it's not going to send the blades all the way to feather, it's going to move them towards a high pitch. But once it gets back to the, whatever the calibrated speed is right here, the flyweights will come back in parallel, it'll close off that port, and it'll maintain whatever oil pressure is in the dome at max RPM, typically somewhere around 2200 RPM. But if it starts to overspeed again, as soon as it starts to overspeed, those flyweights will open and pour a little more oil out, and pour a little more oil out. So it'll sit there and kind of do this to keep the speed right at the max RPM setting. It's automatic, not controlled in flight. However, there is a test switch on it that this can trick it into operating early. So there's the flyweights, the pilot valve, and oil goes back to the prop. Put it all together, you get something that looks like this. So I think we'll kind of talk about this and leave off here. So you can see our governor, along with the beta control valve, is controlling oil pressure, ultimately going out this line, which provides pressure to that prop dome area. Okay, here's our piston, our feathering spring, our counterweights. Okay. You can see there's a linkage here from the dome as the dome moves in and out, which is what drags the blades. That pushes and pulls these linkages that move that feedback ring right here, the propeller slip ring, and that's what provides that feedback during beta mode operation for the beta valve. And then where our overspeed governor is here, if the pressure is too high here and it's causing this to go to fine pitch and it's overspeeding, that will open and allow oil to dump back to the gearbox, which then will drive the prop to a higher pitch, higher blade angle, and a lower RPM.